Hello friends, welcome to engineering tutorial. In today's video we are going to discuss some question on signal flow graph method. Okay, we will calculate or determine the transfer function of a system using the concept of signal flow graph. Okay, so this is the first question. We'll discuss around 4 to 5 questions related to signal flow graph. So this is question number 1. So here we have the signal flow graph. Okay, RS is the Laplace transform of the time domain input and CS is the Laplace transform of the output. We have to determine the transfer function CS by RS using Mason's gain formula. Okay, I have already posted videos related to signal flow graph basics, Mason's gain formula, so you please check out those two or three videos in order to understand the basics and then come to this video. Okay, so according to Mason's gain formula, the transfer function of a system using signal flow graph is given by the expression summation of k equals to 1 to n forward path number k, path factor of forward path k, the kth forward path, by the graph determinant. Okay, so here we have to go individually and find out each of the following terms. First, the number of forward paths, then their path factors, then we have to determine the number of loops, the number of 2 non-touching loops, 3 non-touching loops, and then we have to put the respective values. Okay, so first let us go for the forward paths, the number of forward paths. Okay, so the definition of a forward path says that it is a collection of branches, a group of branches connecting the input node and the output node in a single path traversed in a single particular direction with no node being repeated more than once. Okay, no node should be repeated. So if we look at this signal flow graph, we have only this one forward path. Okay, it has only one forward path, R1, 2, 3, 4, 5, C. Okay, R1, 2, 3, 4, 5 and C. And what is the gain of this forward path? It is the multiplication of the individual branch gains, that is 1 into G1 into G2 into G3 into G4 into 1. So the gain is G1 into G2 into G3 into G4. This is the forward path gain. Now, as there is only one forward path, so let us just remove it from here and write it here in the side. Okay, the gain of the forward path. So only one forward path, P1, it has gain G1, G2, G3, G4, G1, G2, G3, G4. Okay, then now we have to come to the loops. So, okay, so the definition of a loop, it says that it is a closed path which starts and ends at the same node. Okay, with no node repeated. Okay, so I already told you the trick to find out a loop. Look at the nodes. If a node has both outgoing arrow and incoming arrow, like you see this node here, it has an outgoing arrow and an incoming arrow, so it has some loop associated with it. Similarly, this node, look at node number 2, it has an outgoing arrow and an incoming arrow, so it has a loop associated with it. Similarly, this node number 5, it has an incoming arrow and an outgoing arrow, so it must have a loop. Similarly, node number 2 again, it has an outgoing arrow and an incoming arrow, so it has a loop. So let us write the root nodal representation and their gains. Loop number 1, 1, 2, 3, again 1, 1, 2, 3 and 1. See, 1 to 2 to 3 to 1. So the gain is G1 G2 into minus H2, so it will become minus G1 G2 H2. Okay, this is loop number 1. Similarly, loop number 2, 2, 3, 2. Okay, 2 to 3 to 2. So it starts and ends at the same node. The gain is G2 into minus H1, so it will be minus G2 H1, minus G2 H1. Okay, minus G2 H1. Next, this loop, 4 to 5 to 4. You have to always pay attention to the direction of the arrows. See, this forms a closed path, 4 to 5, then in the direction of the arrow again to 4, 4 to 5 to 4. So loop 3 is 4 to 5 to 4 minus G4 H3. Then is loop 4. Okay, loop 4, 2 to 3 to 4 to 5 to 2. Okay, 2 to 3 to 4 to 5 to 2, 2 to 3 to 4 to 5 to 2. What is the gain? The multiplication of the product of the individual branch gains, that is G2 into G3 into G4 into minus H4. So it is minus G2 G3 G4 H4. Okay, so now we have to determine the number of touching and non-touching loops, and then we'll go for the path factor. Okay, so I've already told you in the video related to touching and non-touching loops, that is, two loops are said to be not touching with each other if they have no nodes in common between them. Okay, so if two loops have no common nodes in between them, it means they are not touching each other. Okay, so let us compare each loop with the other loops. First, let us consider loop number 1. First, compare L1 with L2. 1, 2, 3, 1. Here it is 2, 3, 2. So 2 and 3, they are common in L1 and L2. So L1 and L2 are touching. Then we'll compare L1 with L3. 1, 2, 3, 1. Here it is 4, 5, 4. See, no common nodes in between L1 and L3. No common nodes in between L1 and L3. So L1, L3 are two non-touching loops. And what is the gain of the two non-touching loops? Simply we'll multiply the loop gain 1 into loop gain 3. That is, it will become minus G1 G2 H2 into minus G4 H3, which will become minus into minus will be plus, so it will be G1 G2 G4 H2 H3. Okay, then we'll compare loop 1 with L4. 1, 2, 3, 1. Here it is 2, 3, 4, 5, 2. So again 2, 3, 2, 3, they are common. So L1 and L4, they are touching. Next, we'll compare L2 with each of the other loops. We'll go in a systematic way. L2 with L1, see 1, 2, 3. Here it is 2, 3. So L1 and L2 are touching. L2 with 3, 2 3 2, here it is 4 5 4. Again no common nodes, so L2 and L3 are also non-touching loops, two non-touching loops. Okay, two non-touching loops. We'll multiply the gains, so it will become G2 minus G2 H1 into minus G4 H3. Okay, so it will become G2 G4 H1 H3. Okay, so this is the second non-touching loop. Then we'll compare L2 with L4, 2 3 2, 2 3 4 5 2. So 2 3 is the common node, so L2 and L4 are touching. Then L3 will compare with the other. L3 is not touching with L1, so L3 L1 and L1 L3, they are the same. We have already considered that. Again L3 with L2, it is not touching. L2 and L3 and L3 and L2, they are the same, so no need to repeat that. Next L3 with L4, 4 5 4, here it is 2 3 4 5, so 4 5 4 5 common node, so L3 and L4, they are touching. So we have only these two non-touching loops. Okay, these two. Okay, now we have to determine the path factor. Okay, the path factor. Let us write the path, nodal representation of the path. So let us remove these gains. You write these if you want to write, or you can go back. I have to remove because there is no space left, so we'll remove these gains. I'll write the loop equations here. L2, it is 2 3 2, it is L4 2 3 4 5 2. We have to again write the nodal representation of the path to determine the path factor. Okay, there is only one forward path, so it is R1 2 3 4 5 C. Okay, so the path factor delta 1, as there is only one forward path, is 1 minus sum of the loop gains of loops which the path has not touched. Okay, sum of loop gains of the loops which the path, this forward path, has not touched. This is the representation. So we have to determine which loop this path has not touched. It is similar to determining the touching and non-touching loops. We have to find common nodes between the path and the loop. If a particular loop has no common node with this path, then that loop is not touching this path. Okay, so we have to just find common nodes. If we find no common node between this path and a particular loop, it means the path is not touching that loop. Okay, so we'll again compare this nodal representation of this path with the loops. So loop number 1 is 1 2 3 1, and path 1 nodal representation R1 2 3 4 5 C. So 1 2 3 1 2 3. Okay, 1 2 3, here it is also 1 2 3, so it is the path 1 is touching loop 1. Similarly with loop number 2, it is 2 3 2, here it is 1 2 3, so 2 3 2 3 common nodes, so P1 is touching L2. Similarly path 1 with loop 3 4 5 4, here 1 2 3 4 5, so 4 5 4 5 common, so P1 is touching with L3. Next here it is 2 3 4 5 2, here it is 2 3 4 5 2 3 4 5 common nodes, so P1 is touching L4. So P1 is touching all the loops, so the path factor is, for forward path P1 is 1 minus 0 since it is touching all the loops, so it is 1. Okay, so we have got everything. Now just we have to put the values. Okay, so as per Mason's gain formula, the transfer function is given by, as per this signal flow graph, there is only one forward path, so it will be P1 delta 1 by delta. This is forward path number 1, it is path factor of that forward path, and this is the graph determinant. So what is the graph determinant? It is 1 minus sum of individual loop gains plus sum of gain products of two non-touching loops. Two non-touching loops. As there are no three non-touching loops, the equation it will proceed until this. So let us first determine the equation for delta. It will be 1 minus sum of the individual loop gains that we just determined, that is L1 plus L2 plus L3 plus L4. You can rewind it, or if you have noted it down, then you can refer to it. 1 minus L1 plus L2 plus L3 plus L4. I have already calculated the loop gains. I wrote the individual loop gains, so it will be minus G1 G2 H2, sorry, there will be no bracket, 1 minus G1 G2 H2 minus G2 H2 minus G2 G3 G4 H4 minus G4 H3. These are the loop gains of the four loops that the signal flow graph has. Okay, 1 minus sum of the individual loop gains. This part is over. Sum of the individual loop gains, L1 plus L2 plus L3 plus L4, as there are only four loops. Now the gain products of two non-touching loops. Okay, the gain products of two non-touching loops, it means L1 L3 plus L2 L3. Okay, the two non-touching loops which I just wrote here, L1 L3 plus L2 L3. Okay, so the gain products will be G1 G2 G4 H3 plus G2 G4 H1 H3, G2 G4 H1 H3, the two non-touching loops. Okay, so now we have to put this determinant here. Okay, so this is the graph determinant. Now we have to complete this expression. So the transfer function will be P1 delta 1. P1 is the forward path gain, which is G1 G2 G3 G4 into the path factor is 1, we calculated, as the path is touching all the loops, by the graph determinant which we calculated, which will be 1 minus G1 G2 H2 minus G2 H2 minus G2 G3 G4 H4 minus G4 H3 plus the two non-touching loops, which is the sum of the two non-touching loops, G1 G2 G4 H3 plus G2 G4 H1 H3. Okay, this is the expression for the transfer function. Now you can open this bracket, all the minus terms, it will become plus, because minus into minus is plus. You can write it down, you can simplify it further. Okay, so this is how we determine the transfer function of the given system represented by the signal flow graph. Okay, so I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics, instrumentation and communication engineering. Have a great day. Thank you very much.